Okay, so we've seen a couple of examples using the method of characteristics. What we're going to see in this example is a situation where something can actually go wrong and we're not able to solve the PDE. So this is going to be an interesting example and is already going to show big differences between PDEs and ODEs. So let's turn to that now. This is question 9. This is question 9 from the notes. Okay, so we're just going to do everything exactly, try to follow along exactly like we've done before. So first, I'm just going to draw the XY axis just because it's fun to watch me struggle to draw a straight line on the Bamboo tablet. For some reason, vertical is a little better for me than horizontal. I don't know why. Well, whatever. Ordinarily, I don't want to change that, but we'll see. This is not going to work. Okay. So x dot of s, that's the thing that's multiplying the partial derivative of u with respect to x. So in that case, this is 1. X of 0 is x naught. Oh, actually, first let me draw the curve x 4x. Okay, so again, that's just going to be y is equal to 4x. So 1, 2, 3, 4. And let me. Okay, so this is the Cauchy curve, the curve on which the Cauchy data lies, is what I mean by that. So this is y is equal to 4x. I'm just going to get rid of this part because that just is not right. Looks really bad. Okay. So now the y equation is going to be the thing multiplying by the partial derivative of u with respect to y, which is 4. And again, I want this initial point, x naught, y naught, to lie on this curve. So I'm going to put 4x naught here. And again, z dot is just going to be, this part right here is always sort of the z dot. So z dot is going to be equal to 0. And then z of 0, remember, z of s is defined as u. It's just the solution along the curve, along the characteristic curve. So z of s is equal to u of x of s, y of s. So z of 0 is just going to be u of x naught, y naught, which using this up here is going to be x naught. Okay, so now let's see what's going to happen. So if these are the characteristics. If I take a point, a generic point in the plane, I'm going to call this AB. Remember, the whole idea is I want to find the characteristic curve that goes through it and kind of trace it back to this Cauchy data. And then I'm going to solve the equation along this curve right here, because it reduces to an ODE along this curve right here. And from that, sort of piece together the solution for the whole plane. Okay, but notice what's going to happen for this problem. Maybe some of you have already seen it. So what is the characteristic curve? Well, the characteristic curve has slope 4/1. In other words, the characteristic curve through this point is parallel to this black line here. So 1, 1, 2, 3, 4. So what this means is that they never intersect. So these two curves, the characteristic curves, don't intersect I'm going to call this the Cauchy curve. This is probably I've never heard anyone else call it this, but I'm going to call it the Cauchy curve, meaning the curve on which we have the Cauchy data. Okay, so the characteristics don't intersect the Cauchy curve. So I can't sort of take a generic point in the plane here and follow it back to the Cauchy curve. That's just not going to work for this problem. Well, so what can I do instead? So let's try to think through some other options here. So I know that the solution will be constant. So I can do let's look back at the level set method. So let me think about the level set method. And this terminology is also probably mine as well. I don't know of anyone else that calls this the level set method. But if I look at the level set method, well, what are the level sets going to be? Well, the characteristics are given by this equation right here is parallel to the vector 1, 4. So in other words, it's going to be parallel to the vectors. So the level sets are going to be the lines y is equal to 4x plus b, or in other words, it's going to be the sets where y minus 4x is equal to a constant. Okay, so if I just look at the PDE part and forget about the Cauchy data, then this tells me that a solution u of xy is going to be equal to f of y minus 4x. Okay, so any equation of this form, any function of this form, I mean, will satisfy the PDE. But does it satisfy the Cauchy data? So does this function satisfy this Cauchy data, which I have circled in red? Well, let's see. If I do u of x 4x, according to the Cauchy data, this needs to be equal to x. But if I plug it into my candidate solution, well, y is equal to 4x, so this is going to be 4x and then minus 4x, which is equal to f of 0. F of 0 is a constant, so this cannot be equal to the function, x. Okay, so what this says is so there is no solution There's no solution to this problem. Okay, so notice this is a very, very simple PDE. It's a linear PDE with constant coefficients. It's homogeneous. This is about the sort of simplest PDE that we can possibly have, yet there's no solution to it. And so this is one of the biggest differences between PDEs and ODEs. In ODEs, we have all of this huge theory about the existence of solutions to ODEs. Here we have a very simple ODE, and there's not a solution to this ODE. Another very robust theory with ordinary differential equations, in addition to the existence of solutions, is the uniqueness of solutions. Okay, and so now we're going to answer the question, or ask the question, if we can actually find a solution. In other words, instead of x, is there some function that we can put here for which there is a solution? If there is a solution, what does this say us? What does this tell us about f? So let's think through this now. So I've kind of overloaded the f here. So if my function satisfies the PDE, then u of xy has to equal to g of y minus 4x for some function g. And I'm going to use this Cauchy condition to kind of give me some information about what g needs to satisfy. If I satisfy the Cauchy condition, then I have f of x needs to equal u of x 4x, but u of x 4x is just equal to g of 0. Okay, so in other words, if this is satisfied, if I want to find if I want an equation for which there is a solution, f of x needs to be equal to g of 0. In other words, f of x needs to be constant. So yes, the answer is yes. If f of x is just equal to some constant. If f of x is just equal to some constant, then this is going to work. Well, if f of x is equal to, so in other words, if f of x is equal to some constant, then this is going to work. There is going to be a solution. Okay, so let's think a little bit more about this. So f of x is equal to some constant, g of 0, so g of 0, it needs to be some function. So if f of x is just some constant, so let's actually maybe rewrite this equation a little bit, or rewrite the Cauchy condition. The Cauchy data should read u of x 4x is equal to some constant. Okay, and so the solution is going to be u of xy is equal to some function g of y minus 4x. And what do I need? I need to have g of 0. G is just going to be some differentiable function, continuously differentiable function that satisfies G of 0 is equal to C. Okay, so now all that G needs to, so C is given in the problem now. So all G needs to satisfy needs to be a continuous function such that G of 0 is equal to C. As long as G is a continuous function with G of 0 is equal to C, that's going to be a solution to the PDE. Well, there's many different functions such that, many different continuous functions with G of 0 is equal to C. Just think about it. I mean, just think about how many different functions you can satisfy where G of 0 is equal to C, but it's continuous and continuously differentiable. Okay, so what this says is even for this very simple problem, there's a solution. So if I looked at question 9, this very simple problem, there's not a solution. We altered it in question 10. We altered the Cauchy data in question 10 to get a problem for which there is a solution. But notice what happens in question 10. It's not a unique solution. And again, this is a very simple PDE. So this just illustrates that we do not have the uniqueness and existence theorems for PDEs that we do for ODEs. The other thing that this illustrates is there's going to be a problem when the Cauchy curve is parallel to the characteristic curve. So the characteristic direction is 1, 4 in this problem, is the vector with components 1, 4. The Cauchy curve is parallel to that curve. So whenever we have a situation where the characteristic direction of the PDE is parallel to the Cauchy curve, there's going to be a problem, and this illustrates that. And we'll see some of this in upcoming problems.